Hi, everyone. In this presentation, we introduce HaptoMapping, Visuo-Haptic Augmented Reality by embedding user-imperceptible tactile display control signals in a projected image. This work was conducted by the researchers here. Our research motivation is building a Visuo-Haptic Augmented Reality system that can render visual and haptic content independently by keeping spatial and temporal consistencies. The essential technology of our study is to use pixel-level visible light communication (PVLC) to control haptic devices. It enables us to control haptic devices at a pixel level. Also, it reduces the latency to present vibrations and enables us to render visual and haptic content independently. Visuo-Haptic displays are displays that can present visual and haptic information by keeping the temporal and spatial consistencies. One early approach to this is to use an optical combiner as a visual display and grounding haptic device. They can present haptic information on virtual 3D objects, but require to enclose the user's view by the optical combiner. Another way is to embed a haptic display into a visual display. Users can interact with the screen without covering the user's field of view, but the workspace is limited to 2D surfaces. Also, using projection and the light-controlled haptic device is an effective way to maintain those consistencies. They projected time-modulated light using a DLP projector. Haptic devices present vibrations by receiving the projection light and simply amplifying it as vibration signals. It can present haptic information corresponding to the received position, but it cannot render visual and haptic content independently due to the direct conversion. This is a summary of the related work. Projection plus light-controlled haptic display has several advantages, but the rendering of visual and haptic content is limited due to its controlling process. We aim to overcome the limitation using PVLC. PVLC is one of the communication technologies that can embed binary data into each pixel of projected images using fast flashings of binary images. In PVLC, a high-speed DLP projector modulates the luminance of each pixel by displaying a sequence of binary images. We can extract binary data by observing the temporal changes of luminance in each pixel. On the other hand, people cannot notice the fast flashings due to the temporal resolution of humans. All binary images in a frame are projected within 20 milliseconds, and repeatedly projected. This is the configuration of our system. When a user touches the projected surface, a photodiode receives the luminance of the pixel and sends it to the microcontroller. Then, we get the embedded control signal by decoding received light signals. The microcontroller sends vibration patterns through vibration storage or directly from the microcontroller. Finally, the device presents the vibration pattern to the user's finger corresponding to the position. This is a demonstration to check whether the device can receive information at pixel level. We embedded X and Y coordinates into each pixel instead of haptic control signals to get the touching position. We can see that the device can receive the pixel-level information embedded in a projected image without perceivable latencies. This shows the developed haptic devices. We first developed finger-worn and stylus devices. These haptic devices are designed for presenting realistic textures on illuminated 3D models. They have a single photodiode to get PVLC embedded control signals and a single actuator to present haptic sensation to a user's fingertip. We also developed an arm-mounted device. It is designed to create a stroking sensation for online social touch situations. It has 6 modules comprising a photodiode and an actuator. The modules are arrayed on a user's forearm. It also has a screen to project images on the device. We developed some applications using the HaptoMapping system. We first designed a texture design support system that can present various textures, both visually and haptically. Preparing real textures burdens users, and it is not easy for testing texture samples on 3D surfaces. This system helps users to easily test various textures on 3D surfaces. We also developed an online touch system. In this system, a local user can feel the remote user's touch using hand projection and our stroking creation device. The device is comprised of 6 models and each module creates vibrations corresponding to the projected hand. This system allows users to touch again indirectly, who have been unable to meet each other due to external effects such as health quarantine. This is the summary of the presentation. We aim to build a VHAR system that can render visual and haptic contents independently by keeping the spatial and temporal consistencies. To achieve this, we controlled wearable haptic displays using the pixel-level visible light communication technique. As a prototype system, we have developed a PVLC projection system and 3 haptic devices which are finger-worn, stylus, and arm-mounted devices. Then we introduced a design support system and online touch system as applications. For more details of this research, please visit our paper. Thank you.